Good afternoon, Shankal. Okay, I have started recording. Mm, I hope my screen is visible. Okay, right. So, last class we started codes, we saw weighted codes, and then we did a detailed analysis on the BCD codes, that is addition, subtraction. We did the same thing with even with the gray codes also, right? The reflective codes we saw, and then sorry, XS3 codes we saw, and what is the rule for addition and subtraction we saw in the last class. Today what we will do is we'll continue with the codes. We'll continue having seen the two types of codes already. What are the codes we saw in the last class? We saw BCD codes. In BCD, we saw 8421, and in fact 2421 also we saw, and then we saw biculinary codes, right? And then we saw XS3 codes. In 8421, we saw all the arithmetic operations, how to add, how to subtract using complements, that is 9's complement and 10's complement. Then we saw XS3 codes also, XS3 addition and subtraction. Okay. Please note that the XS3 subtraction, either you can apply this particular rule of, remember this particular rule, which is very, very important. If you are getting a borrow, then you will subtract. There is no borrow, then you will add. You can also perform the same subtraction using 9's and 10's complement in XS3 subtraction also. So, yes, and then we saw negatively weighted codes also, 84 minus 2 minus 1 codes. You should note that half of the, after the half of the codes, they are complement of each other. Hence, these kind of codes are also called as complement codes. Not the biculinary codes, but the 2421 and 84 minus 2 minus 1 codes. We'll continue with the XS3 codes. As I've already said that we are slightly slow. That's okay. I think we can manage it later. But the objective is we should not rush and cover it in a hurry. Okay. My only worry is I would like to have some sync between your tutorials and lecture, and similarly between lab and your lecture. Between tutorials and lecture, obviously sync is happening, because as soon as we complete this, your Monday tutorial will be based on these codes only. And then with regarding to the lab, sorry, it will take some time, right? So once we complete these codes, because you cannot have any practicals on these codes, right? So that is why we have it on the gates. So once we start the gates, then I think we will catch up. Okay, coming back to the concept on gray codes, we saw what is a gray code is in the last class, right? What is a gray code? Gray code is a code, sorry. Yeah, gray code is a code which changes by only one bit between the successive consecutive bits, consecutive numbers. In this particular case, 0 changes to 1, and similarly from 0, 1, only the MSB changes. So the sequence of bits, if you see, first is 0, I'm just writing the decimal bits, decimal equivalents, 1, it changes to 3, and then 2, right? But all we need, we are not at all bothered about this decimal equivalent. No need to bother about this. You have to just check whether the bit is changing only by one bit or not. As I have already said in the last class, that these are not at all suitable for arithmetic operation, because you add this 3 plus 1, obviously you know that it is 4, but you cannot apply the gray code for arithmetic operation, which will result in a wrong value and you will get confused. Similarly, there is some property of this particular gray codes. What is that particular property is? I'm going to read this, but you will not again understand. But when we put some value to this n, then you will understand. The n LSBs for 2 power n through 2 power n plus 1 minus 1 are mirror images of those from 0 to 2 power n minus 1. What does it mean is, please note here, now study in the reverse. From 0 to 2 power n minus 1. What is 2 power n minus 1? It is exactly half the values. They are mirror images of numbers starting from 2 power n. After 2 power n minus 1, what is the number? It is 2 power n. So 2 power n to 2 power n plus 1 minus 1. Let us put some value, then you will understand. Please recall that the 2421 and 84 minus 2 minus 1, they are complementing codes. Complementing codes in the sense, after half the codes, they are complement of each other. But here the difference here is, the gray codes are the mirror images of your codes. Let's put some value. Now, if say for example, if we have, I don't know what's not writing. Yeah. Yeah. If you
Excuse
put,
me, sir.
yeah, please.
Are you sharing the slides right now?
I'm sharing the slides. Is it not visible?
Yeah. Maybe it's not visible for me
Yeah,
also.
I think maybe you can restart and then come back, Pradyum.
Yes, sir.
I'll wait for rhythm maybe. Or just to threaten the people who are joining late, let us do something only for this class. Let us stop the lobby. Then everyone will come on time. Okay. Yeah, this is a disturbance, but still okay. Let's continue. Okay. Now, if say for example, let us put some value. Let's put n equal to 2. The two LSBs of 2 power n is what? 4. 2 power n plus 1. N is 2 here. 2 power 3 is 8 minus 1 is 7. 0, 2 power n here, n is 2, so 4 minus 1 is 3. Okay, now let us read from the reverse. From 0 to 3, that is the two LSBs of 0 to 3 are mirror images of numbers from 4 to 7. I hope now it makes some sense. Let's take an example here. Say if I've created a table already, I've created a table. Okay, Pradyumna has joined. All right. Yeah, people have started pinging. See, they are all latecomers. Okay. Let them wait for a few minutes, then they will get tensed. 3. All right. So now, if you look at gray codes, the two LSBs here, what are the two LSBs? Consider 3 bits, only then it will be clearer to you. The two LSBs here, right, are mirror images of bits from 0 to 4. You see here that this is how the gray code is. First, let us create a gray code and then let us come back. For 1 bit, 0 changes to 1. For 2 bit, here again, there is a only 1 bit change. 0, 0 gets changed to 0, 1. Similarly, 0, 1 gets changed to 1, 1 because only this particular 0 gets changed to 1. Similarly, for the next consecutive bits, this 1 will change to 0. Okay. Now, similarly, let us consider a 3 bit. The first bit is 0, 0, 0. Second bit is 0, 0, 1. Why? Because this 0 has changed to 1. Now the second bit is this 1 will not change. If it changes, then what will happen? It will be 0, 0, 0 again. Instead, this 1 will be as it is. The 0 gets changed to 1 here. Okay. So this 0 gets changed to 1, and the next bit sequence is this 1 gets changed to 0. Only one bit will change. Similarly, in the next bit, this 0 gets changed to 1. Then here this 0 gets changed to 1. Then this 1 gets changed to 0. And then again this 1 gets changed to 0. Right? You see in this complete bit sequence, only one bit changes. Similarly, let us see the 4 bit and then let's come back. 0 gets changed to 1. 0 gets changed to 1. 1 gets changed to 0. 0 gets changed to 1. 0 gets changed to 1 here again, 1 gets changed to 0 and 1 gets changed to 0. Please note that we are not at all touching the MSB bits. When MSB bit will change is only after you complete half the decimal codes. So it is a 4 bit, so total possible combinations are 16 codes are possible. So what is half of it? It is half of it is going to be 8 codes. So 8 codes means from 0 to 7 you will have one kind of a code. And then after 7 your MSB will change. MSB bit will change, and after this your MSB bit will not change. Now exactly the reverse will take place. You see here 1 has changed to 0, right? Now here 0 will change to 1. After this 6, in 6, 1 got changed to 0 from 5 to 6. Now 0 will change to 1. So 0 will change to 1. Similarly, here 1 will change to 0. Exactly the reverse will take place. 1 will change to 0. 0 will change to 1. 1 will change to 0. And finally, 1 gets changed to 0. Okay. Now, what is the observation that you need to make here? Right? So one observation is for every consecutive bit, only one bit will every consecutive binary word, only one bit will change. Okay, so that is the first observation. Second observation is, as mentioned before, let me clear these highlights. Exactly, they are mirror images. After half the binary codes, there will be exactly the mirror image. That is only the last. If n is 2, then last it's actually n minus 1 LSBs. If your bit number is 2, then 2 minus 1 LSBs will be a mirror image. Okay. If n is 3, then 3 minus 1, that is 2 LSBs will be mirror images. If n is 4, then 3 LSBs will be the mirror images. Let's see here. Let's go from 4 bit, then you will understand better. Let us consider n equal to 4. For n equal to 4, last 3 LSBs, that is last 3 LSBs will be mirror image of the other bits. What is the mirror image? You see here, you put a mirror like this here. 7 and 8 will be a mirror image. Only the 3 LSBs, please note, not the MSB. 6 and 9 will be mirror image. 5 and 10 will be mirror image. 4 and 11 will be mirror image. 3 and 12 will be mirror image. 2 and 13 will be a mirror image. Similarly, 1 and I think 14 will be a mirror image. Likewise, 0 and 15 will be a mirror image. Okay. Now let us go back to 3 bits. For 3 bits again, these two will be mirror images. 1 and 1 will be mirror image. 0, 1 will be mirror image. And 0, 0 will be a mirror image. And likewise, for 2 bit, these 2 LSBs, that is, if n is 2, then 2 minus 1 will be a mirror images. So 0 and 0, they are mirror images. Like here again, the mirror image will be, there will be no mirror image, because if n is 1, 1 minus 1 is 0, there will be no mirror image here. Okay, so that is what is the rule for these gray codes. Okay, that's allowed. Okay, now Let's move on. Now, how do you convert? These are the gray codes. So we have spent considerable time on the gray codes. Now, how do you convert a binary number to a gray code? Say, for example, I have a binary number, some random number, 1010 to gray code. You want to convert this into gray code. Simple. The rule says that the MSB bit will always be the same, right? So this bit will always be the same. Now, what is this particular bit? This bit is nothing but 1. Okay. Now, going from left to right, that is left to right, you add each adjacent pair of binary code bits to get the next gray codes. See, as I said, this is going to be a disturbance. Yeah. Now, what you need to do is, going from left to right, add each adjacent pair of binary bits to get the next gray code. If you are getting a carry, discard it. Now, what is 1 plus 0? 1. 0 plus 1 is 1. 1 plus 0 is 1, right? So this will be the gray code, the equivalent gray code for this binary number. So this is a binary number, this is a gray code number. Now let's take another example. So 10110, you have to discard carry, don't forget this. You have to discard the carry if you are getting a carry. Okay. You see, as I said, it's a disturbance, but we have to do something. We cannot accept people joining after 17 minutes and 20 minutes. Okay. Now, this is a binary code. We need to convert this into gray code. What we will do, we will copy this one as it is. We copy this one as it is as 1. Now, this 1 is added with 0. 1 plus 0 is 1. Again, the 0 plus 1 is 1. 1 plus 1 is 1 plus 1 is 1 0. We will discard this carry. So it is 0. And then 1 plus 0 again is 1. Right? So this is the binary code and this is your gray code. Maybe one more example. So this 1 is copied as it is. Or let us not look at this example. Right? Let us not look at this example. Let us write on our own so that you will remember better. So this one, I copy this one as it is. Or I'll write here. I'll copy this one as it is. What is 1 plus 1? It is 1 0. I'll use 0 and I will discard the carry. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. Okay. So this is what is the equivalent gray code for this binary number. Both are same, right? So this and this, they are same. Now let us look at gray code. Let us look at the reverse. How do you convert gray code to binary codes? Now, if you are having this particular gray code, what is the rule? What is the rule here is it's slightly different. You copy the MSB as it is. If this is the gray code, I am writing it in some other color. Okay. I'm copying it in some other color. So this is the gray code 11101. What is the rule is MSB is same as in gray code. So you copy the MSB as it is. Now you will add this particular number. You will add this particular number with the next bit of your gray code. So what is 1 plus 1? It is 0, 1. So you discard the carry and you put 0. What is 0 plus 1? It is 1. 1 plus 0 is 0 and 0 plus 1 is 1. You will see that we have reached our, or did I make a mistake? So 1 is there as it is. 1 plus 1 is 0, 1. So I use 0 as it is and then discard the carry. So 0 plus 1 is 0 plus 1 is 1. 1 plus 0 is 0, 1. 1 plus 1 is 0, right? So you see here that we have reached our original gray code here, the original binary number here. So let's take more example here. This is a given gray code. This is a given gray code. You need to convert this into binary. We need to convert this into binary. Ayala Karthik, you came late and you are disturbing like this. Okay. All right. So how do you convert a gray code to a binary? A gray code to a binary, you will copy this one as it is, right? You will copy this one as it is. Then this 1 plus 1 is 0, 1. So we will write 0 and then we'll discard that 1, right? Now what you do is you add the 0 with this particular 0. 0 plus 0 is 0. Then you add this 0 with this 1. 0 plus 1 is 1. This 1 plus 1 is 0 and you discard the carry 1. So this is how you do by gray code to a binary code conversion. Now let us do the same thing as the last example here. 1 0 1 0 1 1 1. So you copy the 1 as it is. This 1 plus 0 is 1. Then 1 plus 1 is 0 discarding carry. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0 discarding the carry. 0 plus 1 is 1. 1 plus 1 is 0 discarding the carry. So this is the equivalent binary number for the given gray code number. Any doubt? Any doubt? Okay. Next, move on to the other codes. Alphanumeric codes. As the name implies, what is an alphanumeric code is?
Hello.
Yeah. Hello.
So can you give an example of binary to gray?
Yeah. I thought somebody is playing. Yeah, I'll give you. Binary to gray. Yeah, okay. So let's take some number, random number. 1 0 1 1 0 1 0 1. Yeah, some random number. You need to convert this into a gray code number. Okay. So the given thing is a binary number. Ayala Karthik. Again. Okay. So we need to convert this into binary number. Copy the MSB as it is. Copy the MSB as it is. Now what you do is you keep on adding like this. 1 plus 0, 0 plus 1, 1 plus 0, likewise. So 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1. Right? So this is the equivalent gray code for a given binary number. Yes, please.
Are you writing something? It's not like you're not sharing.
I think Pradyumna, you have got some problem with your net.
It's not visible.
It's not visible to me as well.
Oh, I see. Okay, then I'm sorry. Then I'll repeat. I'll just, yeah. Is my screen visible now?
Yes, sir.
Yes.
Okay. I'll repeat again. Okay. No issues. Okay. I have just taken a random number. 1 1 0 1 1 0 1 1 1 0 0 0. So just some random number. So this is a binary number, and how do I know that this is a binary number? I'll write its base. I need to convert this into a gray code. Always the gray code, your MSB is copied as it is. Okay. Then what should I do is I must keep on adding the consecutive bits. What is 1 plus 1? 1 plus 1 is 0, 1. I'll use 0 and discard the carry. Now 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0 discarding carry. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0 discarding carry. 1 plus 1 is 0 discarding carry. 1 plus 0 is 1. 0 plus 0 is 0 and 0 plus 0 is 0. Right? So this is what is the gray code. Right? Any doubt? Have I cleared your doubt?
Yes, sir.
Siddharth? Okay. Maybe just for verification, you can do the reverse also. Let us do, and you know that this is a gray code. If you want to convert to binary, then what is the process? If you want to convert to binary, then you must get the original code, right? So let us check whether we have done it rightly or not. Again, to convert to binary, what I am doing here is I am converting this to binary. Here what I did is I converted into gray code. If I convert this to binary, I must get the original code. So what I do is I copy the MSB as it is. Now I add this one with this 0. 1 plus 0 is 1. Again with this one, I am going to add this one. So 1 plus 1 is 0. 0 plus 1 is 1. 1 plus 0, 0. So 1 plus 0 is 1. And then 1 plus 1 is 0. 0 plus 1 is 1. 1 plus 0 is 0. Have I made a mistake? Or have I done a mistake here? I think I have done a mistake here. So 0 plus 1, 1, 1 plus 1, 0. Yeah, I think I have done some mistake here. Okay. All right. So maybe I'll do it again. I'll do it again. I'll do it slowly. So this is 1 here. 1 plus 0 is 1. 1 plus 1 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0. 0 plus 0 is 0. 0 plus 0 is 0. I think we got the original number. Yeah. This and this, they are exactly matching. And this is how you convert from gray to binary and binary to gray. Yeah. Okay. Now, next is alphanumeric codes. Now, why you want to have an alphanumeric codes is because alphanumeric codes mainly they are used as an input codes. Normally, as the name implies, what is an alphanumeric code is you will have an alphabet as well as the numeric numbers in your alphanumeric codes. Okay, so to communicate along with the numbers, both alphabets and symbols are used. Now these alphanumeric codes, as I said, it has got both numbers as well as the characters. Now if you say numbers, then what are the numbers? The number symbols that you know are, you know from 0 to 9. They are the number codes. And how many digits you have? You have 10 digits. And how many alphabets are there? Alphabets are from A to Z, and there are 26 alphabets. So an alphanumeric code is a code which consists of both alphabets and numerical digits. So total of 36 codes are available. If you want to represent 36 codes, then how many bits are required? Normally 2 power 5, you know that it is 32, right? So if you are using a 5-bit representation, then you can cover only 32 symbols that includes alphabets and numbers. If you use 2 power 6, then you can represent 64 number of symbols. though there are only 36 alphabets and digits, but the rest of the things will be unused. So you see how many things are unused. 64 minus 36, close to 8, 28 bit positions or bit combinations are unused if you are using a 6-bit position. So IBM was the one who started off using this alphanumeric codes because they were the one who were making these computers that particular time. Now, as you know that when you type, you not only use alphabets and numbers, you will have additional characters also, right? So you will have a space bar, you will have a lowercase number, you will have a uppercase number, you will have a different symbols like question mark, comma, full stop. All those things are also included in the remaining 28 bit positions, 28 bit combinations. So the 64, when you use 6 bits, then you can use up to 64 symbols. So the other symbols that are used they are the special symbols that are used, for example, comma, question mark, space, etc. Now this alphanumeric codes also, there are two different types of alphanumeric codes. One is called as an ASCII code. It is called as ASCII. What is ASCII is? It is called as an American Standard Code for Information Interchange. Normally they are pronounced as ASCII. And this ASCII is also, there is an extended version of ASCII. So ASCII is one type of a code. And then the other type of a code is called as the EBCDIC code. Normally this ASCII code is the universally accepted code because why? Because it's, when these computers started, IBM was a monopoly in that particular field. So they were the one who introduced these ASCII codes and it became universally accepted also. Later on, there were multiple computers manufacturers that came. One such computer was Enigma. You might have heard about it. They started using about this EBCDIC codes, but still currently also what we follow is we follow this ASCII codes. As mentioned, as I have already mentioned, these are the universally accepted alphanumeric code. Why? Because they were mostly used in computers and almost all electronic equipments. The reason being, IBM was the only manufacturer or a monopoly manufacturer during that particular time. Now, what is this particular ASCII code and how many code combinations are possible? In this particular example, we saw that if you use 6 bits, then you can use 64 bits. Now, normally people started using 7 bits and 8 bit positions. So 7-bit and 8-bit architecture of their system. So nowadays what you use is you use 128-bit architecture, right? So you can have so many number of symbols for representation. So what is this ASCII code is? ASCII code will have 128 characters, right? Not only the characters, it will have symbols also. Now maybe what you can do is if you want to pass away your time, just count how many symbols are available in your keyboard, right? So that will tell you what kind of bit configuration is your system is. Okay, so if you, for the ASCII code, they used 128 characters and symbols. When it is 128, it means that 2 power 7 is 128, and they were using a 7-bit binary code to represent these characters and symbols. As an example, the code for A is given as 1000001. So this is a code for A. Likewise, when we used to study, we used to remember all the ASCII codes for all the 128 characters. I mean, that is how that particular time is. I think I should not allow at this particular time, right? 2:35. I should not allow, I believe. Yeah. So just for, okay. All right. So it's a very simple example. Let's come back. Now, what is an extended ASCII code? Extended ASCII code is, in ASCII, you know that there are 128 codes, right? In extended ASCII code, you will have additional 128 codes. So if you have additional 128 codes, how many codes are possible now? 256 codes are possible If 256 codes are possible, then what should be the size of the bit configuration? It should be 2 power 8 bits. So this extended architecture, normally this was produced by adopted by IBM, right? So when IBM manufactured, they wanted, there was an overflow that was taking place, and there were less number of symbols they were able to use. So in order to do that, they created then 8-bit architecture. 8-bit architecture in the sense they had 8 different bit combinations, right? And what is EBCDIC? EBCDIC is called as an extended binary coded decimal interchange code. Extended binary coded decimal interchange code. Okay. Now these are used to represent 64 bits code only, right? Not 128 or 256 codes. It's only 64 bits, and they will have an 8-bit code word, and at the same time they have a parity bit also. What do you mean by a parity bit? If, say for example, if it is an 8-bit, similar to the sign bit, how many? 1, 2, 3, 4, 5, 6, 7, 8-bit. If this is an 8-bit code word, the first bit, the MSB bit here, this MSB bit is used to represent the parity bit. What do you mean by parity? I will tell you now. Similar to sign bit you had, what? Sorry. If, say for example, you have 1, what does it mean? It is a negative number. If it is 0, it is a positive number. Likewise, they introduce something called as a parity bit. What is a parity bit is? Parity bit will check how many number of ones are there in your bit architecture. How many zeros are there in your bit word, right? So why is it necessary to check number of ones or number of zeros? Normally we won't check for zeros, but we will check for ones. We will always, there are two kinds of parity checking. What is the need for this particular parity checking is to check the error in the code, right? So what is a parity bit? This is an extra bit of information included in the message to make the total number of ones as either odd or even number of ones. So parity can be classified as odd and even. To make the total number of ones as odd, if your architecture is such that you follow an odd parity architecture, then it means that this MSB will be adjusted automatically such that you have odd number of ones. Say for example, I have 0, 1, 1, 0, 1, 1, 0, right? So if, say for example, your computer is designed to work on an odd parity architecture, then it will check for number of ones you have. How many number of ones you have? You have 1, 2, 3 and 4 number of ones. So which means that, but since your architecture is an odd parity architecture, it will append 1 to 1. So now you see that the complete code word will become an odd parity architecture. Say for example, your computer is an even parity architecture. It will check for the number of ones. There are 4 ones here. So it will automatically append 0 to word, telling that it is an even parity word. Why this is required? Why this is required is, this is normally required for correcting the errors and detecting the errors. Now in case of this EBCDIC codes, they have this parity architecture, and if you want to represent A, in case of ASCII code, the A representation is given by 1000001, right? Now what you have done is, you have appended one more parity bit here. So since this is a odd parity architecture, you have added 1 to it. Okay, so you have added 1 to it. So now the EBCDIC representation of A is 11000001. Okay, and why it is used? Why it is used is, it is used for error detection and correction. So there is a special advanced level course in ECE called as error detection and correction course, which extensively uses multiple methods of data bit correction and detection. Now you have to detect the error also, you have to correct the error also, right? Because why? Everything that we transfer now, everything is digital. So which means if I am speaking now, you are not receiving an analog signal. The way I am speaking is analog, but the one that gets converted into your system it is a digital. The one that is getting processed and which is sent to you, everything is digital. So it is very important that you first detect the error, and at the same time you have to correct the error also. So during a data transmission, normally these digital bits that we interchange, they changes from 0 to 1 or 1 to 0 due to multiple reasons, due to noise. Say for example, I'm using a Wi-Fi, right? The Wi-Fi signal, it reaches multiple, there is 103 people are here, it reaches each one of you without any error. Okay, so if say for example, I say some word as hi, then due to noises, due to all these digital interchanges, this I will get changed to Jai, right? So if this happens here, what I'm trying to say. So we must first detect the error at the source end itself and correct the error also, right? So this is very important normally in digital transmission techniques. Now there are multiple methods to first detect the error. What are the multiple methods is, as just we mentioned, the parity method, then there is a checksum method, checksum method, then the block parity method, there is a 5-bit code method, biquinary method. You must recall that we used this biquinary methods in World War II, right? So this is an error detection method of using biquinary codes. Then ring counter code, right? So there is a ring counter method. So we will at least see one or two types of methods of error detection. And what are the different types of error correcting codes are? There is a, if say for example an error has occurred, your system must automatically identify that there is a error in the code, and then it must correct the code and send back to you. So based on that, there are three different kinds of error correcting codes. One is called as a 7-bit Hamming code, 15-bit Hamming code, 12-bit Hamming code. Likewise, in addition to this, you can have any number of bit Hamming codes. It is not mandatory that only 7, 5, 12 are possible. There can be a 20-bit Hamming code, there can be a 40-bit Hamming code. So any bit combinations of Hamming codes are possible. Now, I will just take some additional time today because I need to complete this error correcting course so that you can attempt your tutorials. Okay. Now first let us see the first method, which is called as the parity method. What is a parity method? You know that there are odd parities and even parities, right? I've already explained you what is an odd parity and even parity is. Now, in the parity method of correction, we will add the parity bit to our MSB, which normally this EBCDIC code, which we just saw, already incorporated this parity code, right? So here, if there is no parity code, we will add a parity code. As you know that there are two kinds of parity codes, odd parity and even parity. Normally this parity bits, they will get changed to either 1 or 0. If it is a odd parity, then what does it mean is it will check for, it will be either 1 or it will 0, such that there is total number of ones in the complete bit set. Okay, so this is total number of ones in the complete bit set. Similarly, if it is you are operating for an even parity, then the parity bit is set to either 0 or 1, such that the total number of ones are even. Let us take a simple example. See, we are going to end the class and people are joining now. Okay. All right. So let us assume that this is the decimal equivalent and 8421 code. We have to detect for an odd parity check or an even parity check. If you are having an odd parity check, then it means that we have to add a parity bit here. Okay. If you are using an odd parity, then how many number of ones are there? 0. So you will add 1 to your parity bit. You will add 1. If you are checking for an even parity, then there are even number of ones. So you will append 0 to it. Now let us take the next code 0001. Number of ones in the odd parity is already 1. So which means that if you are checking for an odd parity, your odd parity MSB will be 0. If you are checking for an even parity, it will be 1. For the next bit 0010, number of 1 is odd. So your odd parity MSB bit will be 0, and your even parity, if you are checking for an even parity, then your parity bit will be set to 1. So likewise, we set the parity bits. Let's take a random example. So let us take 1111. If you are checking for an odd parity, then already there are odd number of ones. So 0 is set to the MSB. If you are checking for an even parity, then you have to set your parity bit to 1 such that the total number of ones in the code becomes even, right? So this is what is called as an odd parity and even parity. Now let us see if you have any errors or not. Okay, so let me, though you have seen the answers, yeah. All right. So in this code, we have to check for an even parity scheme. We have to check whether there is an error or not. So how many ones are there? It is 1, 2, 3, 4, which means that there is an error in this particular code. Okay, everything is clear. There is no error in this particular code. Why? Because there are even number of ones. Here again, 1, 2, 3, 4, 5, 6 number of ones are there, which means that there is no error. Please note that this MSB is a parity bit. Okay, all these are parity bits. Now let us check the last one. How many number of ones? It is 1, 2, 3, 4, 5 number of ones are there. We are checking for an even parity. So which means that your parity bit, this one, must be 0. But you are having 1 here, which means that this code is an error code. This code is an error code. Now let us check for a odd parity. Though you already have the answer, but let us check. This is an odd parity. These are parity bits. We are just checking whether the code here satisfies the odd parity or not. How many number of ones are here? It is 3 plus 2, 5, 6 number of ones are there. So ideally, if you are checking for an odd parity, your parity bit must be set to 0, which means that this code is having an error. Similarly, how many number of ones are here? 1, 2, 3, 4 number of ones in total are there. So ideally, your parity bit must be set to 0. Hence, this is an error code. Here, how many number of ones are there? 1, 2, 3, 4, 5 number of ones are here. So the total number of ones are odd, and your odd parity is already set to 1. So which means that there is no error in this particular code. So now let us check for the sum. What is a checksum method? The second method here is a checksum method, right? What is a checksum method is, when you are transmitting and receiving, you will check for the sum of the bits. For example, if I am sending first 101, then if I am sending 110, what is the sum of this? It is 1, then 1, 1 plus 1 is 10, right? So the total sum when you are transmitting is 1011. Now let us assume that you have transmitted. After you have transmitted, 101 and 110 are again added on the receiver side also. If the sum in the transmission and receiving, if both are same, it means that the bits have been transmitted perfectly all right. If say for example this is changed to 1, then the sum will change, right? So what is 101 plus 111 is 7 plus 5 is 12, right? So 0, 0, 0, 1 plus 1 is 0, 1, 0, 1. Yeah, this is double 1, double 0. So double 1, double 0 is compared with 1, 0, 1, 1. And if the sum is not matching, it means that the data bits will be asked to resend it again such till you get some value equal on both the sides, that is on the transmission side and the receiving side. Right. So this is what is called as the checksum is. But there is a problem with this checksum. What is the problem with this checksum? Say for example, this is 111. Now this here, if it has got changed to 100, still the sum will be same. What is 100 plus 111? This is going to be 1011. So sum is same, but there are two errors here. Right. So these are some of the disadvantages of a checksum method. And next, let us see the error correcting codes. We have already seen that there are multiple Hamming codes which are error correcting codes. There is a 7-bit Hamming code, there is a 15-bit Hamming code, there is a 12-bit Hamming code. Now, what is a Hamming code? If you want to transmit 4 data bits, right? So normally these data bits are represented as D. You see here that it is D, D, D. So if you want to transmit a 4 data bits, there will be 3 parity bits in your word, in your binary code. So you see here, there are 3 parity bits now. Now, what is the position of these particular parity bits? They will always occupy the positions 2 power 0, 2 power 1 and 2 power 2. Let me take a larger example. If say this is you are trying to transmit 4 data bits, right? If you want to transmit here, there are 22 data bits. In this particular example, though this looks clumsy, there are total 22, 1, 2, 3, 4, 5, 5 minus 22 was, there are total 17 data bits here. And if you want to represent 17 data bits, then there will be 4 parity bits. There will be 4 parity bits. Okay. How am I concluding that there will be 4 parity bits is, I'll come back to this point later. Now, each parity bit will check for either even parity or odd parity. Okay. Now, the P1 parity bit will check the binary positions. Let me erase. Okay, this P1 will check the parity bits D3, D5 and D7. Similarly, your P2 parity bit will check P4, P5 and then it will check these 2 bits only. So that is what it is written here, that P1, if you are checking for an even parity, will check for 1, 3, 5, 7 bits. If you are checking for a P2 bit, okay, I'm sorry, I didn't see. Okay, your P2 bit, parity bit, will check for even parity, or even you can check for an odd parity also. It will check the bit positions 2, 3, 6 and 7. Parity bit 4 will check for, it should be 4. Okay, so the parity bit 4, ideally it is a third parity bit, but the bit position is 4th, hence I am writing P4. P4 will check for bit positions 4, 5, 6 and 7. How did I do this? Shall I take a larger example so that it will be clearer to you, right? I hope this Excel sheet is clearer, right? So this is a Hamming bit code. Total 40 codes are 40 bits positions are there. So which means that there will be totally 5 Totally 16 and 32. Yeah, totally there must be 5 different parity bits. As you all know that they occupy bit positions 2 power 0. What is 2 power 0? It is P1. 2 power 2 is P2. 2 power 2 is P4. 2 power 3 is P8. 2 power 4 is P16. And 2 power 5 is 32. Hence P32 is here. Okay, I have not highlighted in color. Maybe I'll highlight with the green color. Yeah. So this is how the parity bits will occupy its position. Now, your P1 here will check for positions, the alternative positions it will check. So P1 position, what is alternative to P1? You skip P2, it will check for D3, D5, D7, D9, D11, D13, D15, etc. P2 will check for what is P2's position. From P2's position, you look at how they are checking. It will check for 2, 3, then you skip 2 more places. 6, 7 it will check. You skip 2 more places. 10, 11 it will check. And 12, 13 it will skip. 14, 15 it will check. So likewise, we keep on checking all the number of bits. Your P2 will be checking. P4, what is its bit position? Its bit position is here. Its bit position is here. So you will check for first consecutive 4 bits. You will skip 4 bits. Then you will add 4 more bits. You will skip 4 more bits likewise. Your P8 will check for where are you getting the P8 position? You are getting the P8 position here. So you will check for 8 consecutive bit positions. You will skip 8 consecutive bit positions and then you will add 8 more consecutive bit positions. Likewise, you will keep on checking till the total number of bits you have. So similarly, P16 will check for where is this P16th bit position. From P16, it will check for 16 bit position. 16 plus 16 is 32, right? So including 16 till 31 it is checking. Till 31 it is checking, right? And similarly parity bit 32, from 32 it will check 32 bits. So this is how these parity bits are assigned their positions. Now coming back to simple problem, I've said a larger problem, then I'm coming back to a simpler problem. So your P1 here, it is checking for 1357. P2 is checking for 2367 and P4 is checking for P4567. Okay. Now let us take an example. I need to encode this particular bit. I need to encode this bit 1101 into a 7-bit even parity Hamming code. Do you have class now after 3 o'clock? Anybody please quickly respond. Do you have a class at 3 o'clock? Hello, do you have any class at 3 o'clock? Shall I continue? Not coming. Okay, great. Okay, then I'll continue anyway. Recording is there, right? So you can see the recording. Okay. So now we need to encode this particular bit 1101 in a 7-bit even parity Hamming code. What does it mean? It means that these are the data bits. These are the data bits, meaning that there are 4 data bits here. Now, what will be the Hamming code configuration? Please note, first you have to identify the parity bit positions. Parity bit positions are from left to right, 2 power 0 position. So this is 2 power 0 position, 2 power 1 position, 2 power 2 position, and then it is 2 power 3 is 8. You don't, it is just a 7-bit parity. So you need not put the 4th parity. Now the data bits will occupy after this. So D3, so this position corresponds to D3, this corresponds to D5, this corresponds to D6, and this corresponds to D7. So we have occupied the data bit positions. All we need to fill is the Hamming code positions. I've already said that P1 will check for, we are checking for an even parity. P1 will check for from this particular bit position. It will check for this bit position, this one, and this particular bit position. P1 will check. So your P1 is checking for 1357, and P1 we do not know what should be this value. And what are the 357 positions? 3 is 1, 5 is 1, and 7 is 1. So we are checking for an even parity. So how many number of ones are already there? There are 3 ones are there. So P1 should be 1 to make it as an even, right? So hence P1 is marked as 1 here. Now coming to P2. Okay, so P1 is marked as 1. Now P2 will check for these 2 bit positions. It will check for these 2. Okay, it will skip 2 and then it will check, right? So it will skip 2 and then it will check these 2 bit positions. Now P2, how many number of ones are there? There are already 2 number of ones, right? So P2 will, since we are checking for an even parity, P2 will be 0. Okay. Now P4. P4 will check for these 4 bit positions. How many number of ones are here? There are already 2 number of ones are there. So P4 will take 0 because we are checking for an even parity here. So this is what is the complete Hamming code. So here the final code here is 1010101. Okay. So this is what is the Hamming code is. Now similarly, let us correct the code. Okay, maybe what we will do is we will we will stop here, and then I don't want to rush again. We will see the correcting codes maybe on Monday. We will skip the problem related to error correction of 7-bit Hamming code, but error detection we have just completed here. Okay, so error correction we will see it on Monday's class. You should be able to do your tutorials except this particular part. Okay, so sorry I have to taken a longer time today, and then if you have any doubts you stay, otherwise you can leave the meeting.